Welcome to our deep dive today. We're going to be looking at protecting our machine learning models. All the time and energy we spend training them. We're diving into this research paper called A Systematic Review on Model Watermarking for Neural Networks.
Yeah, this is a really comprehensive overview of different ways to kind of embed like ownership information into these
Yeah.
model.
Like a fingerprint, almost.
Right.
So the idea is to protect the investment, right?
Yeah.
We're talking about time, resources, data, the expertise that goes into building these things,
Yeah.
especially with, model theft on the rise.
Yeah, increasingly these models are targets either to make a profit off of them
Hmm.
or even sometimes maliciously, right? If you train a really complex model, a competitor can just, come in and copy it, use it for their own purposes.
Yeah. So the paper really gets into two main approaches to this watermarking thing: direct embedding and trigger datasets. Can you break those down for us?
Yeah, so let's start with direct embedding. So the idea here is you subtly modify the model's parameters, like the weights and biases, to encode like a hidden message. So it's almost like you're embedding something in the model's DNA without affecting its performance significantly.
Okay. Interesting. And what about trigger datasets?
Yeah. So trigger data sets involve training the model on a special set of data points that are designed to elicit a unique response. So it's kind of like a secret handshake that only the owner knows. It's like you're embedding like a backdoor, in the model that only reveals itself when you present it with the correct key.
So direct embedding is like hiding a microchip in a device, and trigger datasets are like teaching a dog a secret command. Only the owner knows.
That's a good analogy.
So how do we actually verify that these watermarks are there?
Yeah. So the paper talks about different verification methods, and they can be kind of broadly categorized as white box or black box. So white box verification means you need access to the model's internal parameters, so you can directly inspect like the weights or the biases to see if the watermark is there. And
Mhm.
then black box verification means you don't need access to the internals, but you just look at the model's output when you present it with specific inputs, which are usually like those trigger data points that we talked about.
Okay, that makes sense. Now let's dive into some specific techniques. The paper mentioned quite a few.
Yeah. So the paper presents this whole like taxonomy of watermarking schemes and classifies them based on, like how the watermark is embedded, the verification access you need, how much information you can store in it, things like that.
Like a whole family tree of different approaches.
Exactly.
Okay, cool. So one of the early techniques, it was by Uchida et al. Back in 2017. It embeds the watermark directly into the model's weights. How does that work?
Yeah. So they basically introduce like a small bias into specific weight parameters. And that bias actually represents the watermark.
So you're tweaking those weights ever so slightly to encode your message.
Yeah. And the key here is that they have to do it in a way that doesn't mess up the model's performance too much.
Right, because you don't want to protect it to the point where it's useless.
Exactly. So they carefully select the weights to modify, and they keep the bias really small to try to minimize that impact on accuracy.
So how do you actually check if the watermark is there?
So for this technique, you actually need white box access. So you need to be able to see the model's weights to detect that embedded bias.
Gotcha. What other direct embedding techniques did the paper talk about?
Yeah. So another interesting one is this concept of passport layers. It was introduced by Fan et al. In 2019. And instead of modifying existing weights, they actually add new layers to the model that are specifically designed to contain the watermark information.
So it's like a secret compartment built right into the structure.
Yeah. Right. And these passport layers are designed in a way that if you try to remove them or change them, it will, mess up the model's performance.
Oh, so you could verify ownership just by looking at how well the model performs without needing to like peek under the hood.
Exactly.
So that's black box verification.
That's right.
Pretty clever. Are there any examples where they use like cryptography to make the watermarks more secure?
Yeah, definitely. Um, Adi et al. In 2018, they used cryptographic commitments for verification. They create this like trigger set of abstract images, and they train the model to classify these images in a specific way.
Okay. So the way the model responds to these weird images is like the secret handshake.
Yeah. And because they use these cryptographic commitments, it guarantees that the watermark can't be forged or tampered with. So it links it to the owner in a way that you can't really fake.
That's a smart way to do it. It brings in all the, proven stuff from the cryptography world.
Exactly.
Now, what about techniques that actually change the training data itself, not just the model?
Yeah, so there are some methods that embed the watermark in the training data. For example, Guo and Pak Konjak back in 2018, they proposed a method to embed the owner's digital signature directly into the training data.
Wait, how do you embed a signature in data?
So they subtly modify a subset of the training images, and then they train the model to classify those modified images differently than the original ones.
Ah, I see. So the watermark is revealed by how the model reacts to these tweaked training samples?
Exactly. And only the owner would have the original data and know how it was modified, so it creates the strong link between the owner and the model.
That makes sense. The paper also talked about using adversarial examples as triggers. Can you explain that?
Yeah. So adversarial examples are like these inputs that are specifically designed to fool a model. And Lemaire et al. In 2019, they figured out how to use those as triggers. So they trained the model to respond in a certain way to these adversarial examples, and that becomes the watermark.
So it's like you're exploiting the trickery of adversarial examples to hide your watermark.
Exactly. And
Yeah.
because these adversarial examples are, so strange and difficult to create, it makes the watermark harder to detect and manipulate.
So much going on in this field.
Yes,
It's
yes.
like there's so many creative approaches.
Yeah, and it's constantly evolving too. People are coming up with new techniques all the time to make the watermarks stronger and more reliable.
I'm curious about one technique in particular. It's called entangled watermarking. It was proposed by Gia et al. In 2021. What makes that one stand out?
So what's interesting about entangled watermarks is that they basically intertwine the watermark with the model's functionality in a way that if you try to remove it, you actually damage the model's performance. It's almost like you're weaving the watermark into the fabric of the model.
Okay, cool. So how do they actually achieve this entanglement?
So during training, they modify the model's weights in this very strategic way. They spread the watermark information across multiple layers, so it becomes really hard to just isolate and remove it without messing up the learned representations that the model needs to work properly.
So trying to get rid of the watermark is like pulling a thread that unravels the whole sweater.
Exactly. If you try to tamper with it, the model's performance just tanks.
Pretty clever. Another one that caught my eye is null embedding. It was from a paper by Laff et al. In 2019. What's that all about?
Yeah, so null embedding is really interesting because they embed the watermark in a way that doesn't actually change the model's output or its internal structure in any noticeable way.
Wait, how do you embed something without leaving any trace?
They use this cool trick from linear algebra called null spaces. They hide the watermark information within the null space of the model's weight matrices.
So it's like it's there, mathematically speaking, but it's invisible unless you know exactly where to mark.
Yeah. It's like a secret message encoded in the mathematical structure of the model.
Makes it really hard for an attacker to find and remove it.
Exactly. Even if they have white box access, it's incredibly difficult to detect or remove.
That's pretty impressive. I'm starting to see just how many different ways there are to approach this watermarking problem.
Yeah, the research paper really shows the creativity that people are bringing to this challenge of protecting models.
All right, so we've seen all these different ways to embed these digital fingerprints into our models. But now let's switch gears and talk about the attackers, right? How do they try to break these watermarks? What are some of the ways attackers try to get around these watermarks?
Yeah, so the paper goes into a bunch of different attack strategies. It's like an ongoing arms race, right? As researchers come up with new defenses, the attackers figure out ways to break them. And then, new defenses pop up and so on.
Right, it's cat and mouse game.
Exactly. So it's important to know what these attacks are so we can design watermarks that are more resilient.
So let's talk attack strategies. How do they categorize these things?
So they break them down into a few key types.
Okay, cool. Hit me with them.
All right, so one common approach is called watermark suppression. Basically, the attacker tries to hide the watermark's presence during verification without actually removing it from the model.
So like masking the watermark, not erasing it.
Exactly. One way they might do this is by trying to figure out what those trigger data points are, and then they tweak the model so it doesn't respond in the expected way when it sees those inputs.
Like training a dog to ignore a specific command, but only when a certain person is around.
Yeah, good analogy. The watermark is still there, but it's effectively hidden during the verification process.
Sneaky. What else do they do?
Another interesting attack is watermark forging. This is where the attacker tries to create confusion about who actually owns the model.
So instead of hiding the watermark, they're messing with it to make ownership unclear.
Right. There are a couple ways they might do this. One is they might try to recover the original watermark and then claim they own it. Basically like stealing the watermark itself.
Like copying someone's signature and saying, hey, that's mine.
Exactly. Another approach is to try to embed their own watermark on top of the original one. So now you've got multiple watermarks, and it's hard to tell which one's legit.
Muddy the waters with conflicting claims.
Exactly. Then there's watermark overwriting, which is a more direct approach. This is where they just replace the original watermark with their own.
A complete hostile takeover of the ownership marker.
Exactly. They want to wipe out the original watermark and plant their own flag, basically.
And then the ultimate goal for an attacker, watermark removal. Get rid of it entirely.
Right. That's the holy grail of model theft. It's super difficult to do perfectly, but there are some techniques that can get pretty close.
Okay, like what?
Well, one approach is fine-tuning. So they take the stolen model and retrain it on a new data set. The idea is that this retraining will kind of overwrite the subtle changes that were made to embed the watermark.
So they're diluting the signal by adding more noise, basically.
Exactly. Another technique is pruning. They remove parts of the model that they think are unimportant, and if the watermark is concentrated in those areas, they might be able to get rid of it.
It's like surgically removing the watermark from the model itself.
Yeah. That's a good way to think about it. And these are just a few examples, right? The point is, this is a never-ending battle.
Makes sense.
Yeah.
So as researchers come up with better watermarks, the attackers will find new ways to break them, and so on.
Exactly. So we have to stay ahead of the game, right? Keep developing more robust and resilient techniques.
Right. So the paper does a good job of laying out these different attacks so we know what we're up against.
Yeah, definitely. It gives us a framework to think about the threats and how to design watermarks that can survive these attacks.
Okay, cool. Now let's switch gears again. We've talked about how to embed the watermarks. We've talked about how attackers try to break them. Now let's talk about what makes a good watermark in the first place.
Right. So the paper goes through a bunch of requirements for a strong watermarking scheme. It's like a checklist to make sure your watermark is really effective and reliable.
Okay, I like checklist. Lay it on me.
All right. So first up, we've got fidelity. This just means how much the watermark affects the model's original performance.
Right, because you don't want to protect your model so much that it becomes useless.
Exactly. You got to make sure the watermark doesn't significantly lower the accuracy or make the model run slower. It's got to be like a hidden bodyguard, not a ball and chain.
Invisible protection.
Right. Then there's robustness, which is super important. This is about how well the watermark can resist attacks.
Like how well it holds up against all those nasty tricks we talked about earlier.
Exactly. A robust watermark is hard to detect, remove, overwrite, or forge. It can survive all sorts of things the attackers might throw at it.
It's like a lock that can withstand all sorts of picking techniques.
Yeah, exactly. The harder it is to break, the better.
Makes sense. What else is on the checklist?
Okay, next is reliability. This is all about how consistently and accurately the watermark can be detected and verified.
You want to be sure that it always identifies the right owner. No false positives or negatives.
Right, it's got to be like a fingerprint. It should uniquely identify the owner every time.
No mistakes allowed.
Exactly. Reliability is key for proving ownership and making sure the watermark does what it's supposed to do.
Okay, makes sense. Keep going.
All right, then we have integrity, which is closely related to reliability. This is about making sure the watermark doesn't lead to false accusations. You know, it shouldn't mistakenly flag an innocent party as the owner.
Right, like you don't want your fingerprint to accidentally match someone else's.
Exactly. It's about fairness and preventing misuse of the watermarking system.
Gotcha. What's next?
Next up is capacity. This refers to how much information you can actually store in the watermark. It's got to be big enough to identify the owner, but it could also hold other stuff like a timestamp or a unique ID.
So it's not just a yes or no, do you own this model?
Okay.
It can actually hold more detailed information.
Exactly. The more information it can hold, the more useful it is.
Okay.
What else? Then there's secrecy. Ideally, the watermark should be undetectable to anyone who's not authorized to see it, like a hidden message that only the intended recipient can decode.
Makes sense. Keep those attackers in the dark.
Right. Then there's efficiency. The watermarking process, both embedding and verification, should be computationally efficient.
Shouldn't slow down the model too much or make it a pain to use.
Exactly. Efficiency is all about practicality and making sure the watermarking system can be used in real-world applications without being a burden.
Right. Anything else on the checklist?
Last but not least, there's generality. This means the watermark should work across different types of models and data sets. Ideally, it should be versatile enough to handle anything you throw at it.
Not limited to just one specific type of model or task.
Right. Generality ensures that the watermarking system is widely applicable and not limited to just a few niche scenarios.
Okay, that's a pretty comprehensive checklist. It highlights all the different things you have to consider when you're designing these watermarking schemes.
Yeah. It shows you that it's not a simple problem. There are a lot of factors to keep in mind to make sure you've got a really effective and reliable watermark.
All right, now let's shift gears one more time. We've talked about how to embed the watermarks, how to attack them, what makes a good watermark. Let's talk about some of the limitations of this whole approach. What are some of the challenges that researchers are still working on?
Yeah, so one thing to keep in mind is that watermarking is mostly reactive. It helps you figure out if someone's stolen your model, but it doesn't really stop them from stealing it in the first
Right,
place.
it's more like an alarm system that goes off after the break-in has already happened.
Yeah, exactly. So we need more proactive ways to protect models. Like maybe you could detect if someone's trying to copy your model based on their queries or their behavior.
That's a good point. The paper did say that watermarking works best when you combine it with other security measures.
Yeah. It's not like a silver bullet. It's one piece of the puzzle.
Right, got to have a multi-layered defense.
Exactly.
Another thing the paper mentioned is that a lot of these watermarking techniques are kind of focused on specific types of models and data sets.
Yeah, most of the research has been on image classification using these convolutional neural networks.
Right, but machine learning is way more than just image classification.
Right, we've got natural language processing, time series, reinforcement learning, all sorts of stuff. And they all have their own unique architectures and data characteristics.
So we need watermarking methods that can handle this whole spectrum of machine learning.
Yeah, we need techniques that are more general and can work across different types of models and data.
Right, because the real world is messy.
Right.
And that brings us to another challenge, scalability.
Yeah, a lot of the research has been on relatively small data sets. But in the real world, we're dealing with massive data sets, millions or billions of data points.
Right, so can these techniques even handle that much data?
That's a big question. Can you scale them up without making the training process super slow and expensive?
Right, if it takes forever to embed the watermark, it's not going to be very practical.
Exactly. Scalability is a key issue.
The paper also touched on some of the legal and ethical aspects of all this.
Yeah, even if you have a really strong watermark, how do you actually enforce it? What are the legal frameworks for proving ownership and dealing with disputes?
Right, it's one thing to say, hey, I can technically prove this is my model, but it's another thing to have the legal system back you up.
Exactly. We need clear laws and guidelines around all this. And it raises some tricky ethical questions, too.
Right, like how do we protect intellectual property without stifling innovation?
Exactly. And how do we make sure these technologies are used responsibly and fairly?
Lots of big questions still to be answered.
Yeah. It's a fascinating area with a lot of potential, but there's still a lot of work to be done.
All right, so let's wrap this up. Today we went deep into the world of model watermarking. We talked about why it's important, how it works, the different techniques, the attacks, the requirements, and some of the limitations and challenges.
It's a rapidly evolving field, that's for sure.
Absolutely. But the core idea is really important. As machine learning becomes more and more widespread, we need ways to protect the intellectual property that goes into these models.
Right. These models represent a lot of time, effort, and resources. And we need to make sure that the people who create them are recognized and rewarded for their work.
Absolutely. And, watermarking is just one tool in the toolbox. But it's a powerful tool that can help us ensure that the benefits of AI are shared fairly and that innovation continues to thrive.
It's about finding that balance between protecting what's yours and fostering an environment where everyone can benefit from these advancements in AI.
Exactly. So, to our listeners, we encourage you to dive deeper into this topic. It's a fascinating area with a lot of implications for the future of AI. And who knows, maybe you'll be the one to come up with the next breakthrough in model watermarking.
Always room for more innovation and bright ideas in this field.
This has been a deep dive into the world of model watermarking. Thanks for joining us.